Hello, welcome to my talk on Pi Stories, Part 1, Pi Approximations before 18th century. Pi story is one of the most fantastic stories in mathematics. In this series of talks, I will only talk about the main advancement in Pi approximation, rather than the details of the Pi stories. In this part of the talk, I will make a short introduction for the ancient understandings and approximations of Pi, and then move to Archimedes' polygons to approximate Pi. And we will see some important advancement in approximating Pi in the history using polygons. And lastly, the climax of Pi approximations using polygons. In about 1800 BC, it was recognized the relation between the area and the circumference of a circle and the diameter. Euclid proved in the 3rd century BC in his book Elements, the area of a circle is proportional to the diameter squared. The intuitive illustrations for Pi can be made in different ways. The first direct way is use a wheel. First, we can draw the distance on a flat line using the diameter as a unit. And then we can see when rolling the wheel for a whole circle, it would be about 3.14 times of diameter. That means the circumference of the wheel is 3.14 times of diameter of the wheel. In reality, we can still see the distance measurement on a street use such a wheel. Another interesting illustration is the method of Sato Moshan of Japan. In 1698, he cut the full circle to the many equal pieces, the black and the white pieces in the figure. And then he laid out the black pieces in one side, see here, and the white pieces in the other side. And these two sides would fit perfectly as a rectangle. See this. If the pieces are small enough, the height of the rectangle is the same as the radius of the circle. And the length of the rectangle would be pi r, which is half the circumference of the circle. Thus, the circumference of a circle would be 2 pi r. Also, the area of the rectangle would be the length times the height, so it would be pi r squared. Thus, the area of a circle would be pi r squared. In about 1800 BC, Babylonians approximate pi as this expression. This would be equivalent to pi approximated as 3/1/8, so it would be 3.125. This is about 0.5 less than the real pi. And about the same time, Egyptians calculated the circle area using the following approximation, given as the area of a circle is approximated using a square, but the side of the square is reduced by 1/9, so the area is calculated as this. This means if we use pi to calculate the area of the circle, we would have the expression as this. This is equivalent to pi equaling to 3.16. It is about 0.6 larger than real pi. So we can see even in the ancient time, pi approximation are quite good, especially for the area calculation. Since Archimedes in about 250 BC, he used the polygons to approximate the pi, and this method would last about 2,000 years until the end of the 17th century. In principle, the approximation of the circumference can be made using the inscribed polygons like the dashed green hexagon, and the circumscribed polygons, the red hexagon. From this comparison, we can calculate pi between this C1 divided by diameter d and C2 divided by d, or using the radius at of the beast, pi is between C1 divided by 2r and C2 divided by 2r. So if we look at the drawing, we can see for the hexagon n equaling to 6, the inscribed polygon and the circumscribed polygon both are quite different from the circle. If we improve the polygon to 12th, we can see the inscribed polygon and the circumscribed polygon would be much closer to the circle. This would be the principle for the polygon to approximate pi. For the inscribed polygon, we can build the relation for the side of the polygon. Suppose we have an inscribed nth gong, and the side length is indicated by Sn. And then we double the size of the polygon to a 2nth gong, and the side length indicated by S2n, see here, the dashed line. So we can see AB, the length is Sn, and AD is half the length of Sn. So we can see CD is calculated as OC minus OD, so it would give the expression as this. Here we take the radius of the circle as 1, and then we can calculate the size for the 2nth gong. So the side length AC would be calculated as square root of CD squared plus AD squared based on Pythagorean theorem. So put all this relation into the expression, we could obtain the expression between S2n and Sn. We will see when approximated pi, this relation would be much simpler and useful. Now, in a similar way, we look at the approximation use the circumscribed polygons. So similar to the inscribed polygons, we can use the nth polygon with the side length Sn and the 2nth polygon with side length S2n, the dashed line. So we can see AD is calculated by OA minus OD. OD is the radius of the circle, it is 1, and the OA is calculated as the R squared plus half Sn squared, it is given as this, and the dB is half S2n. AB is half of Sn minus S2n. So based on the Pythagorean theorem, AD squared plus DB squared equaling to AB squared, and substitute all these relations into the Pythagorean theorem, we can obtain the relation between S2n and Sm. So from this expression, we can see for the circumscribed polygons, the relation between S2n and Sn is more complicated and is more difficult to use circumscribed polygons to approximate the circle. In fact, there's hardly use circumscribed polygons to approximate the circle unless it is given by the limit of the approximation to the circle. Using the inscribed polygons, we may have two different bases of the polygons. The first one is the polygons based on a hexagon. As we have shown before, if we double the size of the polygon, we have the relation S2n and Sn. So now we can use this relation to calculate the size for the 12th gong, S12 equaling this, since for the hexagon S6 is the same as the radius, it is 1, so S12 will be calculated as this. And we double the size of the 12th gong to 24th gong. We can calculate the side length as this and substitute S12 into this expression. We could have the expression as this. And double the size again, so we have 48th gong. So the side S48 is calculated as this. And if we substitute S24 into the expression, we could have this expression. So if we go on, we can easily find the pattern of the calculation for the different sides of the polygons on the base of a hexagon. So if we have a polygon of side 6 times 2 k plus 1, here k is integer. So for S12, k would be 0, and for 24th gong, k equaling 1, and for 48th gong, k would be 2. And the side for 6 times 2k plus 1 gong, we could have the expression as this. And then following the pattern above, we could have the expression for this gong. Here, we would k layer square root of 2. Once we got the side length as 6 times 2 power k plus 1, and then we can approximate pi as this expression. Here is the side given by this expression. Another example is the polygons based on a square. See here, and the relation between the double sides would be same given as this. Now we have look for the octagon. It would be calculated as this and this. Here we noted S4 is square root of 2. And go on to the 16th gong. We have the expression as this, and substitute S8 into here. We have the expression as this. And double the side to 32 gong. We have the expression as this. So we can see we have very similar pattern as the polygons based on the hexagon. But here, the last square root is for 2 rather than 3. So similarly, if we have a polygon of 4 times 2 power of k plus 1 side, so we can have k for this S8, 0, S16, k is 1, and S32, k would be 2. And the size of this polygon is calculated as this and this. Here we would have k plus 1 layer square root of 2. And once we have the size as 4 times 2 power of k plus 1, we could approximate pi at this expression. Now we come back to look at how the scholars approximated pi. As we mentioned before, Archimedes was the first one to approximate pi using polygons. Archimedes' method is based on hexagon, and what he did was 96 gong to approximate pi. So if we use the formula, we could obtain k equaling to 3. Therefore, S96 would be calculated as this. Here, 3 layers of square roots of 2. And this will give the result for pi as this. So we have 3 decimal places for pi. In fact, Archimedes didn't have the decimal notation in his time, but he could give the result of his calculations based on 96 gongs as the limit of pi. 310 divided by 71 to 1 divided by 7. This equivalent to pi between 3.140845 and 3.142857. In about 263 AD, Liu Hui doubled the size of the polygons Archimedes used, and further to 3072 gong, which corresponded to k equaling to 8 on the hexagon base. So for 192 gong, S192 is given as this. Here k equaling to 4, so we have 4 layers of the square root of 2. So this would give the result for 3.1414524. So 3 correct decimal places. And for the 3072 gong, we have the calculation for S3072 as this. Here we have 8 layers of square root of 2. It would give the result as 3.1415921. So we have 6 correct decimal places for pi. In about 500 AD, Zhu, father and son, doubled the polygons Liu Hui used by 3 times. So Zhu used 24,576 gongs. This equivalent to k equaling to 11. Therefore, S6 times 2 power of 12 is calculated as this. Here, we would have 11 layers of square roots of 2. So we can see the complicated expression, not mentioned the calculation by hand. So this would lead to pi approximation as 3.141592645. This would give 7 correct decimal places for pi. Zhu also gave the simple fraction for approximate pi as 355 divided by 113. So this would give 6 correct decimal places for pi. And this formula was obtained more than 1,000 years earlier than Europeans. The next best approximation with the fraction would be given as this. So here we can see the numerator has 6 digits rather than 3 digits here. For this approximation, we have 9 correct decimal places for pi. In 1424, Persian Jamshid Kashani used 3 times 2 power of 28 gongs, so that would be 805,306,306 gong. So this equivalent to K equaling to 26. This means the calculation would be 26 layers of the square root of 2. Here, I can't give out the expression for side length because it is too complicated. And based on the calculation, he could improve pi to 16 decimal places. Now come to Europe. In 1579, Frenchman François Viard used 3 times 2 power of 17 gongs. That means K equaling to 15. This polygon would have 393,216 sides, and he could improve pi to 9 decimal places. In 1593, Dutchman Adriaan van Rumen used 2 power of 30 gong. That means K equivalent to 27 on the square base. This is more than 1 jillion gong. So he could improve pi to 15 decimal places. And in about 1600, Rudolf van Zuylen, a German who used 2 power of 62 gong, K would be 59 on the square base. So he could improve pi to 35 decimal places. In fact, Rudolf obtained pi to 20 decimal places in 1596 in his book, and then he extended to 35 decimal places. By using hand calculations, it took him about 25 years to arrive at 35 decimals for pi. Obviously, he asked for this pi value on his tombstone in Leyden, and a replica can be seen there. For this particular development, for many years in Germany, pi was also called as the Rudolphine number. In 1630, the last effort for calculating pi using polygons was made by Christopher Grimberger, an Austrian. He used polygons of size about 10 power of 40, so he could improve pi to 38 decimal places. This happened before the calculation of pi using infinite series. This would be discussed in the second part of the series talk.